Hello, my dear students. I hope you all are really doing great. First of all, I welcome you all on this amazing platform of PhysicsWallah English channel. Student, if I talk about today's class, today we are going to discuss a very important chapter of class 11th physical chemistry, and that's nothing but redox titration. So if I talk about the content of today's lecture, we'll start with oxidation state and oxidation number. Then we'll talk about n factor calculation in different cases. Then we'll talk about redox reaction, balancing of redox reaction in acidic medium and basic medium. Then we'll talk about the concept of equivalent weight. Then we'll move to law of chemical equivalence. Then we'll do redox titrations. In redox titration, we'll do simple titration, back titration, double titration, and then we'll talk about volume strength of H2O2, and at the end we'll talk about the hardness of water. So without wasting any further time, let's start our today's discussion. Student, let's start our discussion of redox titration with the first subtopic of this particular chapter, and that is the concept of oxidation state, or the concept of oxidation number, which is there on the screen, right? First of all, can you define it? Student, it can be simply defined as the net imaginary charge appearing on any element after removal of all the bonds from it, heterolytically heterolytic cleavage. Let's try to understand how do we assign oxidation state to any element. Let's suppose I'm having a compound AB, and here the electronegativity of B is more than that of A. Let us assume the electronegativity of B is greater than that of A. Now, if B is more electronegative, can I say because of induction B will have somewhat del negative and A will have del positive? Now, if I cleave this bond heterolytically, if I do the cleavage heterolytically, can I write it like this? A plus 1 and B minus 1. So can I say what's the net charge appearing on element B? Minus 1, right? So what is the oxidation state of B here? Minus 1. What is the oxidation state of A here? Plus 1. Let's take few more examples to understand the concept of this oxidation state in a better way. I'm going to take the example of water molecule H2O, right? It's having a structure like this, OHH. Now, I need to find out the oxidation state of oxygen, hydrogen and hydrogen. What I'm going to do, I'm going to break this bond heterolytically, cleave this bond heterolytically. Between hydrogen and oxygen, which one is more electronegative? Oxygen. So I'll put minus 1 here, plus 1 here. So what's the net charge appearing on this hydrogen? Plus 1. So what's the oxidation state of this hydrogen? Plus 1. Till this oxygen is bonded to one more hydrogen through right side. I'm going to cleave this bond also. Now, as soon as I cleave the bond, I will put minus 1 here and plus 1 here. So what's the net charge appearing on oxygen? Minus 2 now. Is oxygen in the bonded state? No, now oxygen is not there in the bonded state. Is right side hydrogen in the bonded state? Not at all. So what's the oxidation state of hydrogen here? Plus 1. Oxidation state of oxygen here in water molecule? Minus 2. Minus 2 is the net charge appearing on this oxygen atom after removal of all the bonds. Okay, let's take one more example. CH4, H, H, H and H. Now, what you need to do? You need to cleave all the bonds. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. So what's the net charge appearing on carbon atom? Minus 4. What's the net charge appearing on each hydrogen? Plus 1. So what's the oxidation state of hydrogen atom here? Plus 1. What is the oxidation state of carbon atom here? Minus 4. Am I clear, student? Okay, please do copy it. Students, let's take few more examples to understand this concept of oxidation state. Let's talk about cyanide ion. I'm going to take this example, potassium cyanide, right? Highly important chemical. Let's draw the structure of this one. K bonded to C, C bonded to N via triple bond, right? Now, I need to find out the oxidation state of each element in this potassium cyanide. What I need to do? I will break this bond between potassium and carbon. Potassium, more electropositive elements will have plus 1 charge. If I am breaking one bond, carbon, more electronegative, will have minus 1. Now this carbon and nitrogen, they are bonded via three bonds, right? And now between carbon and nitrogen, nitrogen is more electronegative. So if I break this bond heterolytically, all the three bonds heterolytically, can I say I will put minus 3 over here and plus 3 over here? So what is the net charge appearing on carbon atom here? Plus 3 and minus 1. So the oxidation state of carbon in cyanide ion is plus 2. Oxidation state of nitrogen in cyanide ion is minus 3 and potassium, here it's plus 1. Cyanide ion C, triple bond N, and the negative charge is present on carbon atom, right? So we write the structure of cyanide like this. This is cyanide ion. So if you break all the three bonds, minus 3, plus 3, plus 3 and minus 1. So plus 2 oxidation state and minus 3 oxidation state of nitrogen. Student, now there is one more thing to discuss, and that is oxidation state and oxidation number. In the first slide itself, it was written oxidation number, but from the beginning onwards, I am saying oxidation state only. Why so? Is the oxidation state and oxidation number same? Sometimes it's same and sometimes it may not be the same. Basically, oxidation number is defined as the average of oxidation state. Let's try to understand it. Okay, I'm going to take one example, C3O2. Can you draw the structure of this particular compound? Let's draw it. C bonded to C, bonded to C, bonded to O, bonded to O. This is the structure of C3O2. Now, can you tell me the oxidation state of each elements in this compound C3O2? Can you tell me? Please try to attempt it. Student, between carbon and oxygen more electronegative. I need to break this bond. I will put minus 2 over here, plus 2 over here, right? Now, between this carbon and this carbon, is there any electronegativity difference? No. So even though if I break the bond, I will assign 0 and 0. Am I clear? Once again, this carbon and this carbon, once again, 0, 0, right? So this carbon will have the oxidation state 0 only. This carbon will have the oxidation state plus 2 only. This carbon, now this carbon is bonded to oxygen via double bond. I need to cleave this double bond. So it will have a net charge of plus 2 and this oxygen will have a net charge of minus 2. Am I clear? Now, in the compound C3O2, two carbons are having the oxidation state +2 and one carbon is having the oxidation state 0. Right? Now, if someone asks you what is the oxidation number of carbon in C3O2, oxidation number will be equals to, oxidation number is 2 plus 2 plus 0 plus 2 divide how many carbon atoms? 3. So oxidation number is 4/3 and oxidation state of each carbon, two carbon is same, that is +2 and +2, and one of the carbon is having oxidation state of 0. Am I clear, student? Please do copy it. I hope you have copied these things. Okay. Students, now we have a very simple trick to calculate oxidation number of any elements in a compound very easily. Very simple trick. We can do it mathematically or arithmetically. Let's suppose I need to calculate the oxidation state of sulfur in a compound Na2SO4. Okay. I need to calculate the oxidation state of sulfur. Let's try to find out how we can do. Student, I need to calculate for sulfur, so I will assume the oxidation state of sulfur as X. In general, if I talk about alkali metal is having an oxidation state of +1. Alkali metal is having an oxidation state of +1. How many alkali metal atoms are there? 2. So 1 into 2. Okay. And what's the oxidation state of oxygen? In general, in case of polyvalent compound, if more than 2 oxygen atoms are present, in that particular case, oxygen atom will always have an oxidation state of -2. Now, so -2, what's the atomicity? How many oxygen atoms here? 4. Right? And the net algebraic sum or arithmetic sum has to be equals to 0 if it's a ionic compound, because ionic compound is neutral, and in case of neutral compound the net overall charge is 0. So I need to equate it like this: 2 plus x minus 8 equals to 0. So what's the oxidation state? 2 x minus 6 equals to 0. X equals to +6. Right? Can you calculate? Let's do some practice on this calculation of oxidation number, because this calculation is really important. Okay, so I'm giving you few examples or few compounds. You need to calculate the oxidation number of underlined elements. Am I clear? Okay, let's do it. Let's start with C3O2 itself. C3O2, you need to calculate the oxidation number of carbon here. Next one, Na2S2O3, you need to calculate the oxidation number of sulfur. Next one, Na2S4O6, you need to calculate the oxidation number of sulfur here. Next one, KMNO4, you need to calculate the oxidation number of manganese over here. Next one, let's take few more examples. K2Cr2O7, you need to calculate the oxidation number of chromium here. Then K4FeCN6, you need to calculate the oxidation number of iron over here. Next, CuNH3 4SO4, you need to calculate the oxidation number of copper here. Am I clear? So please attempt all these questions. I'm giving you 10 seconds for it. So how many total? 4 and 3, 7. 70 seconds. Please do it. Students, I hope that you have completed all these 7 examples. So shall we start now? Let's start. C3O2. I need to calculate the oxidation number of carbon here. Let's assume the oxidation number of carbon is X. So can I say X into 3? Oxygen in general you can take -2. So -2, what's the atomicity? Into 2. So 3x minus 4 equals to 0. So what is the oxidation number of carbon here? 4 by 3. Right? The same thing we had done there. So the oxidation number which we are calculating is nothing but the average oxidation number. Am I clear? Or average of oxidation state. The formula which we are doing right now, it's basically representing the oxidation number rather than oxidation state. Because here carbon will have +2 and +0 oxidation state. Two of the carbon atom are there in +2 oxidation state and one of the carbon atom is there in 0 oxidation state. Am I clear? Next one, alkali metals will have an oxidation state of +1. +1, what's the atomicity? 2. Sulfur, I need to calculate. I will assume X. So what's the atomicity? 2. X into 2. For oxygen, what's the atomicity here? 3. Oxidation state -2. -2 into 3. Net charge 0, so equals to 0. What's the value of X? 2 minus 6, that is -4. 2x minus 4 equals to 0. Sulfur will have an oxidation state of +2. Na2S4O6. Alkali metal +1, so +1 into 2. Sulfur, I need to calculate. I am going to take it as +x into 4. Oxygen -2. Atomicity 6. -2 into 6. What's the net charge? So +2 and -12, -10. 4x minus 10 equals to 0. So here sulfur will have an oxidation state of +2.5. KMnO4, potassium alkali metal +1. Oxygen -2, atomicity 4. Manganese X, 1 plus X minus 8 equals to 0. So manganese will have an oxidation state of +7. Am I clear? Next one, K2Cr2O7. Potassium +1. Atomicity 2, so +2. Chromium X I can take, so X into 2. Oxygen -2. Atomicity 7, -2 into 7, and that equals to 0. 2 minus 14 minus 12. 2x minus 12 equals to 0. X equals to +6. So here chromium will have an oxidation state of +6. Am I clear? Okay, next one. Okay, now this one is really important. Potassium, what's the net charge? Alkali metal will have an oxidation state of 1. What's the atomicity? 4. So 1 into 4. Now it's an ionic compound. Outside +4 charge. So can I say the net charge on this coordination sphere is going to be -4. Now I need to calculate the oxidation state of iron here. I will take it as X. What's the oxidation state of cyanide ion? The oxidation state of cyanide ion is -1. Total 6. So -1 into 6. What's the net charge appearing on this ion? -4. So X minus 6 equals to -4. So what is the value of X here? +2, because this -6 will go this side, then -4 plus 6, that is +2. So iron will have oxidation state of +2. Am I clear? Next one, CuNH3 4SO4. Student, you need to remember the oxidation state or net charge of few ligands also. Ammonia, water, the net charge is 0. Cyanide, nitrate, net charge is -1. Sulfate, net charge -2. Phosphate, net charge -3. Carbonate, net charge -2. Am I clear? Okay. Copper X. Sulfate, net charge -2. Outside the coordination sphere, net charge -2. So this coordination sphere will have a net charge of +2. Now x plus 0 into 4 equals to +2. So what's the value of x here? +2. So here copper will have an oxidation state of +2. Am I clear, student? Please do copy it. I hope you have copied it. Students, I'm going to write few ligands and I'm going to write the charge, net charge appearing on these ligands. Let's start with nitrates itself. NO3 minus. Net charge is -1. PO4 3 minus. Net charge -3. CO3 2 minus. Carbonate net charge -2. C2O4 2 minus. Net oxalate net charge -2. H2O3 2 minus. Net charge -2. SO4 2 minus. Net charge on sulfate is -2. Cyanide net charge -1. Am I clear? Hydroxide net charge -1. Hydride H minus net charge -1. So please do copy this one also. Students, now let's talk about the general rules for the calculation of oxidation number of certain elements. Student, for alkali metals, let's write for group 1 elements, oxidation state or oxidation number is always +1. Am I clear? For group 1 element, oxidation number or oxidation state is always +1. For group 2 elements, that is alkaline earth metal elements, that is Be, Mg, Ca, Ba, Sr. Let's write it in a perfect order itself. That is Ca, Sr, Ba, Ra. All these will have an oxidation state of +2. Am I clear? Now, if I talk about hydrogen, for hydrogen atom, for H atom, if hydrogen atom is connected to any metal, then it will form metal hydrides. So in case of metal hydride, hydrogen will have oxidation state of -1. That is, if it is connected to M, if I'm having MH bond, in that case, it will have oxidation state of -1. If hydrogen is connected to a non-metal, H atom connected to a non-metal, in that case, hydrogen will have an oxidation state of +1. Am I clear? If hydrogen is bonded to carbon, nitrogen, oxygen, in all such cases, the oxidation state of hydrogen is going to be +1. Please do copy it. Now let's talk about the oxidation state of oxygen atom. Oxidation state of oxygen atom. Student, in case of oxides, if oxygen is there in the form of oxide ion, in that case, oxygen will have an oxidation state of -2 always. In case of peroxide, if peroxy linkage is there, in that case, oxygen will have an oxidation state of -1, like H2O2, right? HOOH. In this particular case, oxygen will have an oxidation state of -1. R2O2, any peroxide. In that particular case, oxygen will be having a oxidation state of -1. In case of superoxide, oxygen will have oxidation state of -1/2. Mainly in case of KO2. You can easily calculate, right? Oxidation number of oxygen is -1/2 here. How? Let's see. I need to calculate for oxygen. So 2 into x plus 1 equals to 0. So what's the value of x? -1/2. Am I clear? So in case of superoxide, oxygen will have an oxidation state of -1/2. Peroxide, oxygen will have an oxidation state of -1. And oxide, oxygen will have an oxidation state of -2. Please do copy it. And you need to remember one very important point, and that we'll use always. If the atomicity of oxygen in any compound is more than 2, if oxygen is present in any polyvalent compound, in that case, oxidation state of oxygen is always -2. Let's write it. If in any compound, atomicity of oxygen is more than 2, then in that case, oxidation number, or let's say oxidation state of oxygen will be -2 only. Shall we take few cases? Let's take KMNO4. What's the atomicity? Four oxygen atoms are there. So what's the oxidation number of or oxidation state of oxygen here? -2. K2Cr2O7. KClO4, HClO4, HClO4, HNO3. In all such cases, H2SO4, right? In all such cases, CrO5, very important one. It's having a butterfly structure, and it's like this: CrO, O, and double bond. In all such cases, in general, it is assumed the oxidation state of oxygen will be -2 only. Please do copy it. Friends, now let's start the discussion of oxidation state of p block element. Okay. In general, the p block element always exhibits variable oxidation state. A certain elements may have different oxidation state. So if I talk about the minimum oxidation state, in case of p block element, the minimum oxidation state is always the number of valence electron -8. If I talk about the maximum oxidation state, the maximum oxidation state is always equals to the number of valence electron. Let's write it. P block elements exhibit variable oxidation state, right? The minimum oxidation state is number of valence electron -8. The maximum oxidation state is maximum oxidation state is equals to number of valence electrons, right? Okay, let's discuss few group elements. Yeah, If I talk about group 18 elements, it's generally there in the non-bonded state. So I'm not going to talk about group 18 elements. Let's start with group 17. If I talk about group 17 elements, we are having group 17. We are having the elements fluorine, chlorine, bromine, iodine mainly, right? Fluorine will always have an oxidation state of -1. It's fixed, -1. Now, if I talk about this chlorine, bromine and iodine, they may exhibit variable oxidation state, right? The minimum oxidation state will be equals to the number of valence electrons minus 8. The number of valence electron is 7. So 7 minus 8, that's equals to -1. So chlorine, bromine and iodine will have a minimum OS equals to -1. What will be the maximum oxidation state? Maximum oxidation state, that is equals to the number of valence electron. The number of valence electron is 7 plus 7, right? So this is all about group 17. Let's take group 16. Group 16, right? The important elements are oxygen, sulfur, selenium, right? O, S, Se, tellurium and polonium. But those elements are not important. Oxygen already we have discussed, right? Oxygen -2, -1, even -1/2, or in general, in case the atomicity is more than 2, in that case it's always -2. We have discussed it. If I talk about sulfur, selenium, they will have variable oxidation state. The minimum oxidation state is going to be equals to how much? Group number of valence electrons, 6 minus 8, so -2. What will be the maximum oxidation state? The number of valence electron, that's equals to +6. Similarly, if I talk about group 15 elements, the elements are nitrogen, phosphorus, arsenic, right? Antimony and bismuth. What will be the minimum oxidation state? Number of valence electron. How much? 5 minus 8. So the minimum oxidation state in case of group 15 elements is going to be -3. What will be the maximum oxidation state? Group 15 elements. 15 elements. Minimum OS oxidation state equals to -3. Maximum oxidation state equals to +5. Similarly, for group 14 elements, the minimum oxidation state will be -4 and the maximum oxidation state will be +4. Am I clear, students? Please do copy it. Friends, I hope that you are crystal clear with this concept of oxidation state and oxidation number. Now let's move ahead. The next thing that we need to discuss is the identification of oxidizing agent and reducing agent in a certain reaction, which all species may act as an oxidizing agent and which one will act as reducing agent. We need to identify that. Okay, we need to understand that. But before that, let's first of all try to understand what do we mean by the term oxidizing agent and what do we mean by the term reducing agent. Student, from class 8, 9th onwards, we have studied this process of oxidation and reduction. Can you tell me what do we mean by the term oxidation? It's nothing but the process of loss of electron. If a certain species loses electron, it is getting oxidized. And in a certain reaction, if a species is getting oxidized, means it will behave as a reducing agent. What it will do? It itself is getting oxidized, so it is going to reduce other. Am I clear? In a certain reaction, if a species accepts electron, basically it decreases its oxidation state, it is getting reduced. And in a certain reaction, if a species is getting reduced, that particular species will behave as an oxidizing agent. It itself is getting reduced but will oxidize the other one in the reaction. Am I clear? Now let's try to understand which all species will act as an oxidizing agent and which all species will act as reducing agent. Let's try to understand. Okay, student, in order to find out which all species may act as an oxidizing agent or reducing agent, First step, what you need to do is the calculation of oxidation state of central atom. Okay. First, you calculate the oxidation state of central atom. Let's take one example, KMnO4. The central atom is manganese. So what's the oxidation state of manganese here? X plus 1 plus X minus 8 equals to 0. So manganese is having oxidation state of plus 7. The next thing, you need to check whether the oxidation state is maximum, whether the oxidation state is minimum, or whether the oxidation state is intermediate, that is between minimum or maximum. Student, if the oxidation state is maximum, can that species afford to lose electron? No, it will not get oxidized further, right? It cannot afford to lose electron. And if it cannot get oxidized further, means it will not behave as reducing agent. So if the central atom of a certain species is having maximum oxidation state, that particular species will always act as an oxidizing agent. The example KMnO4, manganese here is having an oxidation state of plus 7. Plus 7 is the maximum oxidation state of manganese. So it will act as an oxidizing agent. KMnO4, K2Cr2O7. Central atom is chromium. It's having an oxidation state of plus 6. Plus 6 is the maximum oxidation state of chromium. Once again, it will act as an oxidizing agent only. HNO3. So why all these species act as an oxidizing agent? Is it clear? Here, nitrogen is having an oxidation state of plus 5. It's a group 15 elements. Group 15 elements will have a maximum oxidation state of plus 5. So all these species are there in the maximum oxidation state. The central atom of all these species, all these compounds are there in the maximum oxidation state. So all these species will act as an oxidizing agent. Now, if the oxidation state of central atom is the minimum oxidation state, in that particular case, the species will act as a reducing agent. Let's take this one, H2S. What's the oxidation state of sulfur here? -2. The oxidation state of sulfur is -2. Is it there in the minimum oxidation state? Yes. So will it accept electron further? No, it cannot accept electron further. It can lose electron in order to increase the oxidation state. So it can get oxidized only, right? And if it's getting oxidized only, means it will behave only as a reducing agent. Am I clear? LiAlH4. Basically, students, here I am having H minus. This H minus is there in the minimum oxidation state, right? So it acts as a reducing agent. Am I clear? Now, students, we have certain species where the oxidation state of central atom is there in the intermediate state. In that particular case, it may act as an oxidizing agent as well as reducing agent. If the oxidation state lies between maximum and minimum range, in that particular case, it may act as oxidizing agent also, and it may act as a reducing agent also. Am I clear? Please do copy it. Friends, I hope that now you are crystal clear with this concept of oxidizing agent and reducing agent. Let's move ahead. The next thing that we are going to discuss is redox reaction. What do we mean by this term redox reaction? Can you define it? Please define it. Students, please define it fast. Students, basically we define redox reaction as a reaction in which both the process of oxidation and reduction take place simultaneously. A reaction in which the process of oxidation and reduction occurs. both the process has to occur. It's not that only oxidation should occur. Both this oxidation and reduction has to occur, because if one species is getting oxidized, other has to get reduced. Okay, the process of oxidation and reduction occur. Reduction occur, right? Can you tell me few examples of this redox reaction? Can you tell me? Let's write few examples of this redox reaction. What I'm going to do, I'm going to write only the ionic form of this reaction. I'm having Fe plus 2. It's treated with KMnO4, that is MnO4 minus, in acidic condition. Do you remember this reaction? What will happen? This KMnO4 will act as an oxidizing agent. What it will do? It will oxidize iron. It will oxidize iron. The maximum oxidation state of iron is +3. So it is going to get oxidized to +3 oxidation state. This one will get reduced to +2 oxidation state, and I will have water. So this is also a redox reaction, right? Fe from +2 to +3 is getting oxidized. So this is the process of oxidation. MnO4, manganese, is having an oxidation state of +7. It is getting reduced to +2. So it's a process of reduction. It's a redox reaction. Am I clear? Okay. Let's take two more example. Student, I'm having C2O4 2 minus. It's treated with Cr2O7 2 minus in the presence of H plus acidic medium, right? What will happen? It will get oxidized. Chromium is already there in the maximum oxidation state. It's having oxidation state of +6. So it is going to get reduced. I'm going to get product as Cr plus 3. Carbon, what is the oxidation state of carbon here? +3. Please check. 2x minus 2 into 4 equals to -2. So carbon is having oxidation state of +3. The maximum oxidation state of carbon is +4, which we will get in case of CO2. So the product which I am going to write is Cr plus 3 plus CO2 plus H2O. Now, can I say this oxalate is getting oxidized? So this is a process of oxidation. Can I say this dichromate ion Cr2O7 2 minus is getting reduced from +6 to +3 oxidation state? So it is getting reduced. So it's a process of reduction. We'll write lot of redox reaction. You don't need to worry about it. We'll do the balancing of redox reaction in acidic medium, alkaline medium. All these things we'll do. Okay. Let's write one more reaction. I'm having Cu, copper, treated with NO3 minus in the presence of H plus. NO3, it's all nitrogen is there in the maximum oxidation state. So it will act as an oxidizing agent. What it will do? It will oxidize copper. Copper will get oxidized to +2 oxidation state. This one will get reduced, and the product which we get is NO plus H2O. What's the oxidation state of nitrogen here? +2. Here it was +5. So NO3 minus is getting reduced, behaving as an oxidizing agent. Copper in zero oxidation state getting oxidized, so it will behave as a reducing agent. This process is oxidation. This process is reduction. Am I clear, student? Please do copy it. The next thing, disproportionation reaction. It's also a sort of redox reaction only, but here the same element of a particular reaction is getting oxidized as well as reduced. In disproportionation reaction, the same element of a particular reaction, the same element gets oxidized also and reduced also. Let's see. Student, if I take this particular example, H2O2, and it's the product which we are writing is H2 plus O2, right? I'm not balancing this reaction. Okay. Can you tell me what is the oxidation state of oxygen here? Peroxide. So oxygen is there in a oxidation state of -1 here. What is the oxidation state of oxygen here? It's there in the oxidation state of -2. What is the oxidation state of oxygen here? In the free elemental state, right? The oxidation state is 0. Same oxygen is going from -1 to -2. Can I say it is getting reduced? Same oxygen from -1, it is going to 0 oxidation state. Can I say it is getting oxidized? If a species is getting oxidized, it's a process of oxidation, right? If a species is getting reduced, it's a process of reduction. So same oxygen here is getting oxidized as well as reduced. So this particular reaction is a disproportionation reaction. Okay, let me take few more example. Sulfur, oxidation state 0. Here the oxidation state is -2. So from 0 to -2, it is getting reduced. Sulfur, here the oxidation state of sulfur in H2O3 2- is, we have discussed this one, right? +2 oxidation state. So here the oxidation state is +2. From 0 to +2, oxidation number is increasing, process of oxidation. Same sulfur in the same reaction is getting oxidized as well as reduced. So this particular reaction is also an example of disproportionation reaction. Am I clear? Next one. This reaction is really important. Chlorine. In the alkaline condition, we get Cl- plus ClO-, right? If I talk about the oxidation state of chlorine, here the oxidation state of chlorine is 0. Here it's +1. So from 0 to +1, it's the process of oxidation. 0, here the oxidation state is -1. So 0 to -1. So same chlorine is getting oxidized, also reduced. So this reaction is also an example of disproportionation reaction. Please do copy it. Students, let's discuss some more important disproportionation reaction, and these are H2O2, that is H2O plus O2, we have already discussed. And now this reaction, halogen treated with alkaline with OH-, that is treated with base, dilute base. In that case, the product which we get is X- plus XO-, right? 0 to -1, sorry, -1, here +1. So it's also an example of disproportionation. 0 to -1, reduction. 0 to +1, oxidation. Same element getting oxidized and reduced, in an example of disproportionation reaction. So halogen treated with dilute base, we get X- and XO-. Halogen treated with concentrated base plus OH- concentrated. In that case, one of the product is going to be X- and the other one is going to be XO3-. So here halogen will have an oxidation state of +5. It's also an example of disproportionation. From 0 to +5, oxidation. From 0 to -1, reduction. I hope these examples are crystal clear to you all. Okay, student, one more point. Sometimes we'll say conproportionation reaction. What do we mean by this conproportionation reaction? The reverse of disproportionation is conproportionation. If this reaction will occur in this direction, -1 and +5 going to 0 oxidation state, then this particular example will become the example of, or the reaction will become conproportionation reaction. So the reverse of disproportionation reaction is conproportionation reaction. Am I clear? Please do copy it. Friends, moving ahead, the next subtopic which we need to discuss is the concept of valency factor calculation or n factor calculation. One of the most important tool through which we can solve our numerical problem very easily, and one of the most important concept. Okay, so let's first of all try to define it. How do we define it? It's defined as the number of electron transferred per mole of a chemical species in a redox reaction. Number of electron transferred per mole of a chemical entities or chemical species in a redox reaction. Let's write it. Number of electron transferred per mole in a redox process or in a redox reaction. Am I clear, students? Now, let's discuss case by case. Case 1. N factor calculation case 1. Simply for pure elements. Student, if the elements are there in the pure elemental state, if they are not in the combined state, in that particular case, the N factor or the valency factor of element is simply the number of valence electron. Let's write it. For pure elements, for pure elements, if the elements are there in their pure elemental state, means it's not there in the combined state, in that particular case, N factor is nothing but the number of valence electrons. Number of valence electrons. Right? Let's take the example. Sodium. The number of valence electron is 1. So what will be the N factor? 1. Magnesium. 2. Right? Aluminium. N factor. 3. Silicon. N factor. 4. Carbon. N factor. 4. Am I clear, students? So if the elements are not in their combined state, if they are not in the form of, if they are in the pure elemental state, in that particular case, N factor is nothing but the number of valence electrons. Now, if they are in the combined state, then we can have covalent compounds, we can have ionic compounds. So let's discuss case one by one. Case 2. N factor of covalent compounds. N factor of covalent compounds. Covalent compounds. Student, if I talk about the N factor of covalent compounds, in this case, N factor is simply nothing but the covalency. N factor equals to covalency. Am I clear? If I talk about ammonia, what's the covalency? How many sigma covalent bonds are there? 3. So what's the N factor of ammonia? 3. N factor of water. What's the covalency of oxygen here? 2. So N factor of water is going to be 2. CH4. What is the covalency? How many sigma covalent bonds are there? 4. So what's the N factor of methane? 4. Carbon dioxide. Covalency 4. So N factor is going to be 4. Am I clear? So in case of covalent compound, N factor is nothing but covalency, the total number of covalent bonds connected to the central atom. Am I clear? Please do copy it. Valency factor calculation for acids. Students, in case of acids, N factor is nothing but number of replaceable H plus ion. Right? Okay. If I talk about HCl, how many acidic hydrogens are there? 1. So what is the N factor? 1. Replaceable hydrogen is 1. H2SO4. What will be the number of replaceable hydrogen? How many acidic hydrogens are there? 2. S3PO4. Number of replaceable or acidic hydrogen? 3. Right? Let's draw the structure of this S3PO4. The structure is like this. P double bond O, OH, OH, OH. H3P. So students, in case of H3PO4, how many replaceable hydrogens? 3 hydrogens. So what's the N factor? 3. 3 acidic hydrogen. H3PO3. H3PO3. It will have a structure like this. P double bond O, H, OH, OH. How many acidic hydrogen? 2. So here the valency factor in case of H3PO3 is 2. In case of H3PO2, what will be the valency factor? P double bond O, H, H, OH. Right? H3PO2. How many acidic hydrogen? Only 1. So what's the N factor of this H3PO2? 1. N factor of some more acids, H2CO3. Number of replaceable hydrogen, 2. So N factor of that acid will be 2. Am I clear? Please do copy it. Now, N factor calculation for base. In case of base, N factor is nothing but the number of replaceable OH minus ion. N factor or valency factor is nothing but number of replaceable OH minus ions, hydroxyl ions, right? Okay. NaOH. How many replaceable OH minus? Only 1. So what will be the N factor? 1. MgOH whole twice. How many hydroxyl ion replaceable? 2. N factor is going to be 2. AlOH whole thrice. Number of replaceable OH minus? 3. Right? So N factor is going to be 3. Am I clear? Are these things crystal clear to you all? Please do copy it. Now, valency factor calculation for acid base reaction. Let's discuss few cases. HCl plus NaOH will give me NaCl. Okay. Now, if I look at this HCl, so how many H plus is replaced? Only 1. In this particular reaction, only 1 H plus is replaced by the cation, right? So what's the N factor of this acid? 1. What's the N factor of this base? Only 1 OH minus is replaced by Cl, so N factor is 1. Am I clear? Next one. I'm having H2CO3 treated with NaOH and I am getting the product NaHCO3. Okay. In this particular case, can you tell me the valency factor of this acid? You will say, sir, here 2 replaceable hydrogens, so valency factor will be 2. No. If the reaction is given, check how many H plus has been replaced by cations. 2 acidic hydrogen, only 1 acidic hydrogen. So only 1 H plus is replaced by cation. So what's the valency factor here? N factor is 1 here. N factor of this base, only 1 OH minus is replaced by this anion HCO3 minus. Am I clear? So N factor is 1. Now one more reaction. I'm having H2CO3 treated with NaOH and now NaOH, and now the product is Na2CO3. Can you tell me the N factor of this acid? Now both H plus is replaced by the cation Na plus. So in this particular case, N factor of the acid is going to be 2. Am I clear? One more case. Student, I am having H3PO4 treated with NaOH and I am getting Na2HPO4. Let's assume my product is this one. Can you tell me the N factor of acid here? 3 replaceable hydrogen. 1 acidic hydrogen is still here. So how many hydrogen has been replaced by this Na plus? 2. So what's the N factor of this acid here in this particular reaction? N factor is 2. So this is how we calculate N factor in acid base reaction. I hope these things are crystal clear. Please do copy it. Now, N factor calculation for salts, or we can say N factor calculation for ionic compounds. We have studied N factor calculation for covalent compounds. Now it's time to discuss N factor calculation for ionic compounds. Students, in case of ionic compound, N factor is nothing but net charge appearing on cation, or this or is important, anion. Okay, let's try to understand it with this example. NaCl, the cation is having a charge of +1, anion is having a charge of -1. So either we have to consider the charge of cation or the charge of anion, only magnitude, not the sign. So what's the N factor here? 1. MgCl2, what's the net charge on cation? +2. Net charge on anion? -1. Atomicity 2, so -1 into 2. So what will be the N factor of MgCl2? Only 2. We don't need to consider sign. AlCl3, N factor will be net charge on cation +3, anion -3. I have to consider magnitude only. So N factor of AlCl3 is 3. CH3PO4 whole twice. Can you tell me the N factor of this particular compound? What's the net charge appearing on cation? +2 into 3, atomicity 3, or -3 phosphate net charge is -3 phosphate ion PO4, 3 minus into 2. So what's the net charge either on the cationic species or on anionic species? 6. N factor will be 6. Am I clear? Right, student? Okay, please do copy it. ZnCl2, let's take one more example. What's the net charge on cation here? Chloride ion -1 into 2, so -2. So on net charge on cation +2, valency factor will be 2. Please do copy it. Now, N factor calculation in case of redox reaction. Student, in case of redox reaction, N factor is calculated as number of electron transferred per mole of the chemical species. Okay, number of electron transferred per mole. Okay, let us try to understand. I'm having one example, C2O4 2-. It's treated with MnO4-. The product which I am getting is CO2 plus Mn plus 2. Okay, let's see. What's the oxidation state of oxygen? -2, right? So the oxidation state of oxygen is not going to change. What's the oxidation state of carbon here? +3. What is the oxidation state of carbon here? +4. Okay, so now in this particular compound, that is oxalate ion or ion, only the oxidation state of carbon is changing. So now let's try to calculate the N factor of this particular ion. From +3 to +4, what is the change in oxidation state? 1. What's the atomicity of carbon here? 2. So N factor is change in oxidation state or into atomicity, Let's write atomicity. Now, if I talk about this oxalate ion, here carbon is in the +3 oxidation state. In CO2, carbon is there in +4 oxidation state. Change is 1. Atomicity is 2. So what will be the N factor of this compound? 2. N factor is going to be 2. Right? Now let's talk about this one. MnO4 minus. Can you tell me the N factor of this MnO4 minus here? What's the oxidation state of manganese here? +7. We have done it, right? What's the oxidation state of manganese here? +2. What is the change? From +7 to +2, change is 5. What's the atomicity of manganese? What is the atomicity of manganese here? 1. Change 5, atomicity 1. So N factor of KMnO4 or MnO4 minus here is, N factor here is 5 into 1. Am I clear? Please copy it. Students, now let's calculate the N factor in each of the following example. Okay. First, I need to calculate the N factor of KMnO4 and FeSO4 in this particular reaction. Okay, let's try to find out. Student, potassium, will there be any change in oxidation state? For alkali metal, the oxidation state is always fixed. I don't need to bother about this one. For oxygen, if the atomicity is more than 2, the oxidation state is always fixed. So this, for oxygen also, there won't be any change in oxidation state. Only the oxidation state of manganese may change. So let's first of all calculate the oxidation state of manganese in reactant. And it's having -8 + 1 -7, x -7 equals to 0. So +7. If I talk about iron here, iron is in +2 oxidation state. Why? Because sulfate is having a net charge of -2, so +2. Now, if I talk about here, SO4 2-, so manganese here is in +2 oxidation state and iron here is in +3 oxidation state. Am I clear, students? Iron +3. How? Let's see. Let's assume the oxidation state of iron is X. So X into 2 minus 2 into 3. Net charge on sulfate ion. We don't need to bother about the sulfate. We don't need to calculate each and every individual oxidation state of sulfur and oxygen. If I am having a ligand like sulfate, nitrate, simply focus on the net minus charge. Am I clear? Okay. Equals to 0. So 2x minus 6 equals to 0. So the value of x is 3. Iron here is in +3 oxidation state. So this one is getting oxidized and KMnO4 is getting reduced. KMnO4 is acting as an oxidizing agent here. Now, what's the change in oxidation state from +7 to +2? Change is 5. How many atom? 1. So 5 into 1. So what's the N factor here? N factor of KMnO4. That's equals to 5. Now let's talk about this iron. Iron is in +2 oxidation state. Here iron is in +3 oxidation state. What's the change from +2 to +3? Change is 1. How many atoms here? I'm calculating the N factor of FeSO4, not Fe2SO4 thrice. Right now I need to focus here. Okay. What's the atomicity? Only 1. So change is 1. Atomicity 1. So what is the N factor here? N factor will be 1 into 1. That is 1. Now if someone says me calculate the N factor of Fe2SO4 3 in this reaction. Now here iron is in +3 and it is going to +2 oxidation state. Change 1. Atomicity, how many atoms here? 2. So the N factor of Fe2SO4 3 will be 2, whereas N factor of FeSO4 will be 1. Am I clear? Next one. Iodide ion is in -1 oxidation state. Here 0 oxidation state. Change 1. -1 to 0. Change is 1. Atomicity here 1. 1 into 1. So N factor will be 1. Now if someone says calculate the N factor of iodine molecule here from 0 to minus 1, change is 1, atomicity 2. So n factor of iodine molecule will be 2, whereas iodide ion will be 1. Am I clear? Change into atomicity. Change in oxidation state into atomicity. Next one, iodine, 0 oxidation state. Right here, minus 1 oxidation state. Change 1. Atomicity 2. So 1 into 2. N factor will be 2. Am I clear? Next, Na2H2O3. 1 into 2 minus 2 into 3, that is minus 4. 2x minus 4 equals to 0. So sulfur is there in plus 2 oxidation state here. And here if you will calculate, sulfur is there in 2.5 oxidation state. What's the change? Change is 2 to 2.5, 0.5. What is the atomicity? 2. So what will be the N factor here? N factor is going to be 1. Am I clear, student? Please do copy it. Next one, we need to calculate N factor of K4FeCN6. Okay, let's focus here. Plus 1 into 4. Alkali metal is there in plus 1 oxidation state. Atomicity 4, so net charge here plus 4. So net charge on the coordination complex minus 4. We have done this, right? Now here iron is there in the plus 2 oxidation state. Why? Because x minus 1 into 6 equals to minus 4. So x plus 2. In case of cyanide ion, we have studied carbon was there in plus 2 oxidation state and nitrogen is there in minus 3 oxidation state, right? That's why the overall net charge is minus 1. Plus 2 minus 3, that is minus 1. Now here, iron plus 3 oxidation state, carbon plus 4 oxidation state, and here nitrogen x minus 6 equals to minus 1. So plus 5 oxidation state. Potassium, there won't be any change. Iron plus 2 to plus 3, change 1. Loss or gain? Loss of electron. Loss of electron means oxidation, right? 1 loss. What's the atomicity? 1. So 1 into 1. Carbon plus 2 to plus 4. Loss or gain? Loss of electron. Per atom, how many loss? Per atom, 2 loss. Total number of atoms, 6. So can I say total loss 2 into 6. So till yet 1 loss from iron and 6 loss. 6 into 2, 12 loss of electrons from carbon. Nitrogen minus 3 to plus 5 oxidation state. Increase in oxidation state is loss of electron, right? Here also we have loss of electron. Minus 3 to plus 5. What's the change? How many loss per atom? 8. What's the total number of atom of nitrogen here? 6. So total loss 8 into 6. All these species are losing electron. Iron losing 1 electron, carbon net loss of electron 12, and nitrogen net loss of electron 48. So what's the N factor here? If only loss is there, you need to add. If loss gain is there, then you need to subtract. Am I clear? If only gain is there, once again you need to add. Am I clear? Here 48, 12, 60, 61. So N factor of K4FeCN6 in this particular reaction is 61. Okay, next one. KMnO4 plus Fe plus 2 plus H plus. Manganese plus 7 plus 2. This reaction is occurring in acidic medium. Student, always remember, in acidic medium, N factor of KMnO4, N factor of KMnO4 is plus 5. Okay, here this reaction is occurring in alkaline medium, plus 7 oxidation state. If you look here, manganese is in plus 6 oxidation state. Change 1. Atomicity of manganese here, only 1. So N factor in alkaline medium is 1. This is important. You need to remember this one. N factor of KMnO4 in alkaline medium is 1. Acidic medium is 5. Now let's talk about neutral medium. Plus 7 oxidation state, plus 4 oxidation state, change 3, right? So n factor of KMnO4 in neutral medium, n factor of KMnO4 in neutral medium is how much? 3. Am I clear? Please do copy it. This reaction is occurring in neutral medium. So in alkaline medium, n factor is 1. In neutral medium, the n factor is 3. And in acidic medium, the n factor of KMnO4 is 5. Next one. This reaction mainly occurs in acidic medium. Let's calculate the n factor of potassium dichromate here. Plus 1 into 2, 2 minus 14, 12. 2x minus 12 equals to 0. So chromium plus 6 oxidation state plus 3 change 3 atomicity here 2. So n factor of potassium dichromate here will be 6. N factor of potassium dichromate in this particular reaction is 6. Chromium is going from plus 6 to plus 3. So change is 3. Atomicity of chromium is 2. So n factor is going to be 6. Next one. Now, student, if we look at this particular reaction, can you tell me which type of redox reaction is this one? Disproportionation reaction, right? Okay. Now, iodine 0, minus 1, plus 5, right? Loss or gain from 0 to minus 1, gain of electron, right? What's the n factor due to gain? 0 to minus 1, change, n factor reduction. N factor, if I consider only reduction, then 0 to minus 1 change is 1, atomicity is 2. So n factor due to reduction is 2. Now let's calculate n factor due to oxidation only. Iodine 0 oxidation state going to plus 5 oxidation state, change 5, atomicity 2. So n factor due to oxidation, how much? 5 into 2, that's equals to 10. Now in case of disproportionation reaction, the net n factor is n reduction into n oxidation upon n reduction plus n oxidation. So what is the n factor due to reduction? 2. N factor due to oxidation 10, n factor due to reduction 2 plus 10. So it's 20 upon 12, 20 by 12, 5 by 3. So n factor of iodine in this particular redox disproportionation reaction is 5 by 3. Am I clear, students? So I hope this concept of n factor is now crystal clear to you all. Please do copy it. Friends, now moving ahead, the next thing which we are going to discuss is balancing of redox reaction in acidic medium as well as in alkaline medium. Students, here I will simply give you a shortcut, and if you apply the shortcut, you can do the balancing of redox reaction both in acidic medium and in the alkaline medium in less than 1 minute. Let's try to understand. I'm having a reaction Fe plus 2. I'm simply writing the ionic form, okay? So I'm having Fe plus 2 treated with MnO4 minus in acidic medium. The product which I am getting is Fe plus 3, Mn plus 2, and obviously water molecule. Let's do the balancing. Okay. What's the oxidation state here? Plus 2. What's the oxidation state here? Plus 3. What's the change? 1. N factor? 1. N factor is 1 here. What's the n factor of MnO4 minus? From plus 7, it's going to plus 2. Change 5. Atomicity 1. So n factor is 5. Now, in order to balance, the first step which you need to do is to do the crisscross of n factor. So this plus 5 will come here and this plus 1 will go here. Let me write it here. So what I'm going to write, 5 Fe plus 2 plus 1 MnO4 minus plus H plus. Okay, I don't need to bother about this H plus. We can do later on also, or we can write later on also. Plus Mn plus 2 plus H2. Okay, now charge balancing is done. Now atom balancing. 5 iron here, so I need to add 5 iron here. Manganese, manganese done. Now the next step is the balancing of oxygen atom. How many oxygen atom here? 4. So what I need to add? I need to add 4 water molecule. 4 here. As soon as I add 4 water molecule here, how many total hydrogen atom? 4 into 2, 8. So I need to put at 8 over here. Am I clear? First, calculate the n factor, do the crisscross. Once you are done with that, means your charge balancing is done. Now do simply the atom balancing. Okay? Let's practice few more questions. Now let us attempt this particular question. We need to do the balancing in acidic medium. Here you will see in the reactant side there is no H plus, because already this H2S is a source of acid only. Either I can write it as 2H plus and plus S2 minus, or I can simply write it as H2S. Am I clear? So I don't need to write H plus here. Okay. Now, student, what's the n factor of KMnO4 here in this reaction? From plus 7 to plus 2. Anyhow, in acidic medium, n factor of KMnO4 is always plus 5. Plus 5. What's the n factor of H2S here? Oxidation state of sulfur minus 2 going to 0 oxidation state. Change to n factor 2. Do the crisscross. Write 2 here and 5 here. 5 sulfur atom. I need to write 5 here. Already 2K plus I have written. Already then 2 Mn2 plus also I need to write. Right? So potassium balancing done. Sulfur balancing done. Manganese balancing done. Now I need to balance this oxygen atom. How many oxygen atom here, students? How many oxygen atom? 2 into 4, total 8. So how many oxygen I need to add here? Student, I need to add 8 water molecule here. Is the oxygen balancing done? Now total how many hydrogen? 16. Total how many hydrogen here? 10. How many H plus I need to add? 6 H plus. Right? Am I clear, student? So this is how we do the balancing in acidic medium. Step 1. Step 1. Calculate n factor. Calculate n factor. Do crisscross of n factor. Crisscross cross of n factor. Charge balancing done. Now do the balancing of atoms. Once other atoms are balanced, then you need to balance oxygen atom. Okay, and balancing of oxygen atom is done by adding water molecule on the other side, and in the last do the balancing of hydrogen atom by adding H plus. Am I clear? Please do copy it. Next one, student, now we need to understand the concept of balancing of redox reaction in alkaline medium or in basic medium. Here also almost 80% it's same, only we need to add 2 more steps. Okay, let's try to understand it. I'm having ClO minus. What is the oxidation state of chlorine here? X minus 2 equals to minus 1. So X is in plus 2, plus 1. The value of X is plus 1. Chlorine here is in plus 1 oxidation state. What is the oxidation state of chromium here? X minus 4 equals to minus 1. So chromium is in plus 3 oxidation state. Chlorine minus 1 oxidation state. Chromium plus 6 oxidation state. Fluorine from plus 1 it is going to minus 1. What is the change? 2. Atomicity. 1. So what's the n factor? N factor is 2 here, right? From plus 3, it is going to plus 6. Atomicity 1, change 3. So n factor is 3 students. Am I clear? Now, the next step once again is crisscross of n factor. So I will write 3 here, I will write 2 here, right? Now I need to do the balancing. So I will write 3 chlorine here and I will write 2 chromium here. The next thing is the balancing of oxygen atom. Okay, let's do the balancing of oxygen also. 3 oxygen and total how many? 2 into 2, 4. So 4 plus 3 is 7 oxygen here. 8 oxygen here, right? So I need to add water molecule. Which side? This side only. So let me add 8 oxygen here and 4 and 3, 7 oxygen here. So I'm going to add 1 water molecule, H2O, right? Now the next step. This side I'm having 2 hydrogen atom. So here also I need to add 2 H plus. Students, now you may say, sir, this is how we do the balancing in acidic medium. Are all the steps same in basic medium also? I will say 90% steps are same. Only one thing we need to do. We need to focus on the coefficient of H plus. What's the coefficient of H plus here? 2. Now what I am going to do, the next step, I am going to add equal number of OH minus on either side of this reaction, on the reactant side and as well as product side. Okay, let's do it. So what I am going to do, I am going to add 2 OH minus here on the reactant side and 2 OH minus on the product side. Now, so can I write this reaction like this? 3ClO minus plus 2 CrO2 minus plus H2O plus 2OH minus is giving me 3Cl minus plus 2CrO4 2 minus 2H plus and 2OH minus is nothing but 2H2O, right? 2H2O and H2O, right? Now this is my final balanced reaction. And in this final balanced reaction, you will see OH minus and H2O. So this reaction is occurring in alkaline medium. Step up to this H plus, the same step as we have done in the balancing of redox reaction in acidic medium. Only the last step is addition of equal number of OH minus on both sides. Simply look at the stoichiometric coefficient of H plus and add equal number of OH minus on either side. Am I clear? Please do copy it. Next one. Can you do the balancing here? Yeah, you can easily do. Okay. 0 minus 1, change 1, atomicity 2, n factor 2, plus 5, plus 7, plus 5 to plus 7, change 2, atomicity 1, n factor 2, right? 2, 2. Okay. Now let's do the balancing of atom, charge balancing done. 4 chlorine, so I am going to add 4 chlorine here. 2 iodine, I am going to add 2 iodine here. Now I need to do the balancing of oxygen. 6 oxygen, 8 oxygen. I need to add water molecule. I am adding 2 water molecule. Now oxygen balancing done. Am I clear? Now I need to do the balancing of hydrogen atom. 4H. So I am going to add 4H plus. Now I will focus here on this 4H plus. I am going to add equal number of OH minus on both sides. 4 OH minus, 4 OH minus, right? 4H plus and 4 OH minus will give me this one, 4H2O. 4H2O, reactant side, already 2H2O is there. So can I cancel out this one and can I strike it and can I write it like 2 only? So can I write my final balanced reaction? 2Cl2 plus 2IO3 minus plus 4OH minus is giving me 2IO4 minus plus 4Cl minus plus 2H2O. This is how we do the balancing in alkaline medium. Next one, ASO3 minus. If we look at this particular question, actually there was a slight error. Instead of ASO3 minus, you need to take ASO3 3 minus. And now here arsenic will have an oxidation state of +3. It's going to oxidation state of +5. So change to N factor 2. If I talk about this magnetine +7, it's going to +4. So change is 3. N factor is 3. Now I need to do crisscross. So I will write 2 here and I will write 3 here. Right? Charge balancing done. So I will add 3 here. Since 2 magnets, I will add 2 here. Now I need to do the balancing of oxygen atom. Student, if I look here, I'm having 3 into 3, 9 oxygen and 8, 17 oxygen. Here, if I look, I'm having 12 oxygen and 4, 16 oxygen. So I need to add 1 water molecule here, right? Now, by adding 1 water molecule, I need to add 2 H plus here. Since I need to do the balancing in alkaline medium, I will add equal amount of OH minus on both sides. Right? 2H plus and 2OH minus, they will form 2H2O. 2H2O. On right hand side, I am having 1H2O. It will get cancelled, right? 2H2O and 1H2O. Okay, so what will be the final reaction? 3ASO 3 minus plus 2MnO4 minus plus H2O will give me 3ASO4 3 minus plus 2MnO2 plus 2 of OH minus. Right, student? This is the final balanced reaction. I hope this balancing of reaction or balancing of redox reaction both in acidic medium as well as in alkaline medium is crystal clear to you all. Students, now let's talk about this concept of equivalent weight. If I talk about the definition or the standard definition of this equivalent weight, it is simply defined as the number of parts by weight of an element which combines with 1 part by weight of hydrogen, 8 parts by weight of oxygen atom and 35.5 parts by weight of chlorine atom. But this definition is not really important from application point of view. For chemical calculation, we have one important formula, and through that important formula, we can easily calculate equivalent weight of any elements in any reaction. Okay, so let's talk about that also. Equivalent weight of an element is nothing but molecular weight divided by N factor or valency factor. We have learned how to calculate N factor, right? Even for element, for covalent compound, for anionic compound, for acids, for bases, for acid-base reaction, for redox reaction, for disproportionation reaction, for all such things, we have studied how to calculate N factor. Once we know the N factor, can we easily calculate equivalent weight? Equivalent weight is nothing but molecular weight divided by N factor, or we say it as valency factor. Meaning it's same. Either you write valency factor or you write N factor. Am I clear now? Student, in mole concept we have studied moles. And mole is calculated as given weight upon molecular weight, right? Similarly, we have one more important terminology, and that is number of gram equivalents or number of equivalents. Some people say it as gram equivalents, or you can simply say it as equivalents. Equivalents. Either you write it as number of equivalents or you write it as number of gram equivalent. And it is nothing but given weight upon equivalent weight. Equivalent weight, you know how to calculate. Equivalent weight is nothing but molecular weight divided by n factor. Okay, let's write that also. So given weight W divided by molecular weight divided by n factor, right? So this n factor will go up. So W upon molecular weight into n factor. Now this weight upon molecular weight, if we focus here, can I say it's nothing but number of moles? So can I say number of equivalents is always equals to number of moles, or number of gram equivalent is always equals to number of moles into valency factor or n factor. Am I clear? Please do copy this one. Highly important one. Okay, please do copy it. Now, student, through this table, we can easily learn how to calculate equivalent weight of some important chemical or equivalent weight of some important species in highly important redox reactions. Okay, if I talk about the equivalent of MnO4 minus, that is KMnO4 here, right? What's the oxidation state here? +7. It is going to +2 oxidation state, change 5, n factor 5. So if someone asks you what is the equivalent weight of KMnO4 in acidic medium, it's simply molecular weight divided by 5. Equivalent weight of KMnO4 in acidic medium is nothing but molecular weight divided by 5. Am I clear, student? Is this concept clear? Next one. Equivalent weight of KMnO4 in alkaline medium, that is MnO4 minus. Let's first of all talk about neutral medium. It's going to MnO2, n factor, +7 to +4, change 3 electron transferred, molecular weight divided by n factor. What's the n factor here? 3. So equivalent weight of KMnO4 in neutral medium is molecular weight of KMnO4 divided by 3. Similarly, equivalent weight of KMnO4 in alkaline medium from +7 to +6, accepting 1 electron. So if I talk about the equivalent weight of KMnO4 in alkaline medium, it's same as that of molecular weight. Am I clear? Next one. Equivalent weight of potassium dichromate or dichromate ion in acidic medium. From +6 it is going to +3, change 3, atomicity 2, n factor 6, right? N factor here is 6. Equivalent weight is molecular weight divided by 6. 6 electron transferred. Am I clear? So what's the equivalent weight of potassium dichromate? Molecular weight divided by 6. Equivalent weight of potassium dichromate, molecular weight by 6. Equivalent weight of MnO2 here. What's the oxidation state? +4. It is going to +2, change 2, n factor 2. Equivalent weight is molecular weight by n factor, molecular weight by 2. Am I clear? Next one. Cl2, 2Cl minus, change 1, atomicity 2. N factor will be, if chlorine is getting converted to chloride ion, n factor is 2. So equivalent weight will be molecular weight of chlorine divided by 2. Right? Similarly, CuSO4, oxidation state of copper here +2, it is going to +1, change 1, n factor 1. Am I clear? Look, from +2 it is going to +1, change from +2 to +1, change is 1, atomicity is 1, 1 into 1, n factor 1. Equivalent weight, molecular weight divided by n factor, that is equivalent weight, it's same that of molecular weight, right? Okay, next one. This one is really important. H2O3 2 minus. Let me write that. H2O3 2 minus getting converted to S4O6 2 minus. What is the oxidation state of sulfur here? 2, 2.5, change 0.5, atomicity 2, 0.5 into 2, n factor 1 mol. Now can I calculate the equivalent weight here? Equivalent weight is molecular weight divided by n factor. So equivalent weight is same as that of molecular weight, 2m by 2. Basically it's m only. N factor is 1. Clear? Next one, H2O2, highly important. What's the n factor of H2O2 here? From -1 it is going to -2. Change 1. Atomicity 2. N factor 2. Right? If n factor is 2, equivalent weight of H2O2 will be molecular weight divided by 2. Even as if H2O2 is acting as a reducing agent, here this H2O2 is getting converted to oxygen. From -1 to 0, change is 1. N factor is 2. 1 into 2. Am I clear? So n factor is 2. So student, n factor of H2O2 is always 2 and equivalent weight of H2O2 is always molecular weight divided by 2. Molecular weight of H2O2 is how much? H2O2, 32 plus 2 upon 2. How much? So equivalent weight of H2O2 is 17. Am I clear? Fe plus 2 getting oxidized to Fe plus 3. Change in oxidation state plus 1. Equivalent weight, molecular weight divided by n factor. Same. Equivalent weight and molecular weight is same. Student, if n factor is 1, equivalent weight, molecular weight is same. Number of equivalents equals to number of moles. But if n factor is not equals to 1, in that case, equivalent weight is molecular weight divided by n factor. Clear? Have you copied all these things? Please do copy it. Please copy this one also. Now, the next thing that we need to understand is the concept of normality. We have studied molarity. We know that, right? Molarity is nothing but number of moles per liter dissolved in 1 liter of solution. Similarly, normality can be defined as the number of gram equivalents present in 1 liter of solution. Number of gram equivalents of solute present in 1 liter of solution. Number of equivalents or gram equivalents of solute present in 1 liter of solution, right? It can be defined as number of equivalents divided by volume of solution in liter, right? Suppose if 2 equivalents are there in 5 liter, so in 1 liter how many equivalents will be there? 2 by 5, right? So number of equivalents present in 1 liter of solution is nothing but normality. Am I clear? If n equivalents are present in V liter, so what will be the normality? In 1 liter it will be n by V. Am I clear? Okay. Student, if volume is there in terms of milliliter, you need to convert that milliliter into liter. So in that case, you can use the formula normality is equals to number of equivalents upon volume in ml into 1000. You can use this one, right? You can use these formula. Now, okay. Students, we have normality is equals to number of equivalents upon volume in liter. Now, can I write this number of equivalents as number of moles of solute into n factor divided by volume in liter? And this number of moles upon volume in liter is nothing but, this term is nothing but molarity. So can I say normality is equals to molarity into n factor, right? Normality is always equals to molarity into n factor. Let's suppose I am having one normal or one molar H2SO4. It's given the molarity of H2SO4 solution is 1 molar. Can you calculate the normality? If no reaction is given, what's the n factor of H2SO4? 2. So in that case, normality is going to be 1 into 2. So 2 normal. 1 molar means 2 normal. Am I clear? So it's a diprotic acid. Now, one more important point. Student, if I multiply this normality into volume in liter, can I say it's nothing but crisscross? It's nothing but number of equivalents. This is really important. In the titration part, we will use this formula only. Normality into volume equals to number of equivalents. And number of equivalents can also be written as given weight upon equivalent weight. So can I write N into V in liter is always equals to given weight upon equivalent weight. Suppose in some question, if they give us normality, if they give us volume, and then they ask calculate the weight of solute used, can I use this formula? Normality into volume in liter equals to given weight upon equivalent weight. Am I clear? Please do compete. Law of chemical equivalence. What does this law say? It simply says in any chemical reaction, the number of equivalents or gram equivalents of each reacting species are same independent of their stoichiometric coefficient. Let's suppose I'm having a reaction of the type 2A plus 3B giving me 4C plus 5D. What are the reacting species? A, B, C and D. Now according to the law of chemical equivalence, the number of gram equivalents, equivalents of A reacting equals to number of equivalents of B reacting, number of equivalents of B reacting. This word reacting is really important. Equals to number of equivalents of C formed, which is also equal to number of equivalents of deformed. Am I clear, student? In any chemical reaction, the number of equivalents of each reacting species are same. The best thing about this law of chemical equivalence is here we don't need to balance our chemical reaction. Simply we can apply this tool and it simply says number of equivalents of one reactant reacting equals to the number of equivalents of other reactant reacting, and that will be equals to number of equivalents of the product formed. So if I know the weight of one reacting species or if I know the weight of one product formed, we can calculate the weight and all the parameters of all the reacting species provided we know the n factor. So it's very important tool, and with the help of this tool we don't face much problems while solving the questions of stoichiometry. Okay, let's move ahead. Student, let's try to solve this particular question. Find the number of moles of KMnO4 needed to oxidize 1 mole of Cu2s in an acidic medium. Okay, we'll apply this law of chemical equivalence in order to solve this problem. I'm having the reaction KMnO4 plus Cu2s is giving me Mn plus 2 plus Cu plus 2 plus SO2. Right. Okay. Let's calculate the n factor of its species. What's the n factor of KMnO4 here? N factor, acidic medium, right? N factor is always plus 5. So n factor is going to be 5 here. Now, if I talk about this copper, oxidation state plus 1, it is going to plus 2. Loss or gain? Loss or gain? Loss. Change 1. Atom 2. So how many electron loss? 2 loss. So n factor due to copper is 2. Now sulfur is having oxidation state of minus 2 here. And here it is having oxidation state of plus 4. What's the change? 6. Right? Loss or gain? Minus 2 to plus 4. Loss only. Loss of electron is increase in oxidation state. So 6 loss because of sulfur, 2 loss because of copper. What's the net loss? 8 loss. So what's the n factor of Cu2s here? 8. Now, number of moles of KMnO4 needed to oxidize 1 mole of Cu2s. Now, can I apply law of chemical equivalence? If I apply law of chemical equivalence, I don't need to balance this reaction. Okay. So, can I say number of equivalents of KMnO4 will be equals to number of equivalents of Cu2s, right student? Now how do we calculate number of equivalents of KMnO4? Number of equivalents is always equals to number of moles into n factor. Let's assume number of moles is x. What's the n factor? So x into 5 is the number of equivalents of KMnO4. Here the number of moles of KMnO4 is x, n factor is 5, so number of equivalents is 5x. Number of equivalents of Cu2s equals to number of moles of Cu2s. Mole is 1 into n factor. Number of equivalents is number of moles into n factor. What's the n factor? 8. So what's the value of x? 8 upon 5, 1.6. So the moles of KMnO4 required to oxidize this Cu2s in acidic medium is 1.6 mole, 8 by 5 mole. Am I clear? 1.6 is the right answer. Please do copy it. And if we look at this particular question, what given? Weight of NaOH. Weight of NaOH, how much? 1.184 gram. Molarity is also given. That is 0.15 molar. Let's use this equivalent concept tool only, although we can solve it using mole concept tool also, but we'll use equivalent concept here. Student, what's the n factor of NaOH? 1 only. So can I say molarity and normality is same? So normality is 0.15 normal, right? Now we have studied one important formula. Weight upon equivalent weight is equals to normality into volume in liter, right? Am I clear? Now what's the given weight here? 1.184. What is the equivalent weight of NaOH? N factor is how much? 1. If n factor is 1, then molecular weight and equivalent weight will be same. 23, 39, 40 equals to, what's the normality? 0.15 into volume in liter. So from here, can I calculate volume? That's 1.184 upon 40 into 0.15. Right, student? 0.15 into 40. How much? 6. So it's 1.184 upon 6. right? Liter. You can calculate in terms of milliliter, multiply it by 1000. So it is going to be 1184 upon 6, close to 195, let's say, ml. Right, student? I hope you understood it. Please do copy it. Students, moving to the next question which we have on the screen, and the question says, 0.4 molar KMnO4 solution completely reacts with 0.05 molar FeSO4 solution under acidic condition. Perfect. The volume of FeSO4 solution used is 50 ml. Okay. What volume of KMnO4 was used? Very simple question. One liner. Okay. I'm having KMnO4. This KMnO4 is treated with FeSO4. Right, student? I will get MnSO4 plus Fe2SO4 Fe2SO4 whole thrice, right? Okay, let me erase this bracket. This one, yeah. Fe2SO4 whole thrice. Okay, do we need to balance this reaction? No. Now we know the tool of law of chemical equivalence. It says milliequivalents or equivalents of KMnO4 reacting equals to equivalents of FeSO4 reacting, right? Okay, so let's apply that. Can I say number of equivalents of KMnO4 reacting of KMnO4 is equals to number of equivalents of FeSO4, right? Now, how do we calculate number of equivalents of any species? Either weight upon equivalent weight or normality into volume in liter. But student, here volume is given in terms of ml. So instead of using the concept of equivalents, we'll use milliequivalents. What's number of milliequivalent? Number of milliequivalents, MEQ, we write it in short form, that is always equals to normality into volume in ml. Now if the number of equivalents are same, number of milliequivalents will also be same. So can I say number of milliequivalents and number of MEQ of KMnO4 will be equals to number of MEQ of FeSO4. Now what's the number of MEQ of KMnO4? Normality into volume, right? Is normality given? Molarity is given. Now, how do we calculate normality? Molarity into n factor. What will be the n factor here? In acidic medium, n factor is 5, right? What's the n factor of FeSO4? Plus 2, 2 plus 3, change 1, n factor 1 only, atomicity is 1 only, right? Okay. So can I say molarity of KMnO4 into n factor into volume in ml, that is equals to number of milliequivalents of FeSO4, molarity of FeSO4 into n factor into volume in ml. Now molarity they have given as 0.4, perfect. 0.4 into 5 into volume, we don't know, we need to calculate. Molarity of FeSO4 they have given as 0.05. 0.05 into volume, how much? 50 ml. 50. Okay, so 2 into V is equals to 2.5, right student? 0.05 into 50, it's 250, 2 decimals, so 2.5 is the calculation. Okay, please check it. 50 into 5, 250, and 2 points decimal, right? So 2.5. So volume is 2.5 divided by 2, it's 1.25 ml. So volume of KMnO4 required for this reaction is 1.25 ml. Am I clear? Please do copy it. Let's move to the next question. And now this particular question says zero point 0.3 gram of an oxalate salt, that is C2O4 2 minus, some oxalate ion is there, was dissolved in 100 ml. Perfect. The solution required 90 ml of N by 2 KMnO4 for complete oxidation. Perfect. The percent of oxalate ion in the salt. We don't know what's the percent purity, that we need to know. Means 0.3 gram of oxalate salt is there, but what is the exact amount of pure oxalate ion, that we don't know. We need to calculate that one. Okay. So student, if we write the reaction, I will have my reaction as C2O4 2 minus will react with KMnO4. What this KMnO4 will do? It is an oxidizing agent. It will oxidize this oxalate ion. The product which we will get is CO2 plus Mn plus 2. Right? Now what is the N factor of this oxalate ion? Carbon plus 3 oxidation state, carbon plus 4 oxidation state, change 1, atomicity 2, N factor is 2. N factor is from plus 7, it is going to plus 2 oxidation state, N factor is 5. Right? So now we know the N factor. Okay. They have given the volume of KMnO4 and normality. So from here, can I calculate number of milliequivalents of KMnO4? KMnO4, and that's equals to normality into volume 1 by 20 into 90. Right? So it's number of milliequivalents of KMnO4 is 90 by 20, it's 4.5 milliequivalents. So can I say the number of milliequivalents of pure C2O4 has to be C2O4 2 minus has to be 4.5 only. If I apply law of chemical equivalence, number of MEQ of pure C2O4, MEQ of pure C2O4 2 minus will be equals to number of MEQ of KMnO4, and number of MEQ of KMnO4 is 4.5. Now we don't know the normality of this oxalate ion. If we don't know normality, then we have one more tool to calculate, or we have one more formula to calculate the number of equivalents or number of milliequivalents. That is given weight upon equivalent weight into 1000. That is number of milliequivalents. Let's use that one. Weight, we don't know. Weight of pure C2O4 2 minus upon equivalent weight, that is the number of equivalents, into 1000 is the number of milliequivalents, will be equals to number of milliequivalents of KMnO4, and that's 4.5. Now what is the equivalent weight of C2O4 2 minus? What's the N factor here? 2. Molecular weight 24, 64, 88 divided by 2. Equivalent weight is 44. Weight upon 44 into 1000, right student, equals to 4.5. So from here weight will be equals to 4.5 into 44 upon 1000. Right? Now this is the weight of pure C2O4. Now we need to calculate the percentage purity. Percent purity, I will simply write it in the form of fraction. You can do the calculation, right? Can you do it? I don't need to do it, right? Okay. So percent purity will be 4.5 into 44 upon 1000. That is the weight of pure C2O4 2 minus upon weight of sample, that is 0.3 into 100. This is the percent purity. Right? So it's 3, and how much? 4.5 into 44, divided by 3, it's 1.5. 1.5 into 44, 66% purity is there. Am I clear, student? Please do copy it. Students, I hope you are crystal clear with the concept of simple titration. Moving ahead, now let's discuss the concept of back titration. What is this back titration? Let's try to understand. Sometimes while solving the questions related to these titrations, you will see one of the reactant is given in excess, right? How to attempt such questions? Let's try to understand. And this particular concept, we say it as back titration. Back titration. Okay, let us try to understand this back titration with one example. Student, I am going to take two reacting species A and it's reacting with B and is giving me C and D. Now here I am taking B as excess. So in the question it is given B is taken in excess. Let us assume the normality of B taken is N1 and the volume of B taken is V1 ml, right? Now in the question it is given some amount of B is left and now the left amount of B is reacting completely with E and is giving me F and G. Okay, in the question it is given the normality of the reacting species E taken is N2 and the volume consumed is V2. Now they may ask from you, calculate the weight of A reacted. They may ask from you, calculate the weight of A reacted in this particular titration. Let us try to understand. Student, here B is taken in excess. So can I say this A will act as a limiting reagent? A will act as a limiting reagent. Will entire B get consumed in the first reaction itself? No. There will be certain amount of or certain milliequivalents of B left from reaction 1 and the left B which is left is reacting completely with E and is giving me F and G. So from second reaction, can I write milliequivalents of B left equals to milliequivalents of E reacted or taken? And what's the milliequivalents of E taken? N2 into V2 ml, right, student? Now this is the milliequivalents of B left. What was the milliequivalents of B initially taken? Milliequivalents of B initially taken initially was N1 into V1, right? So initially taken this much, right? Left was N2 V2. So how many milliequivalents of B has reacted in reaction 1? Here the milliequivalent left was N2 V2, initially taken is N1 V1. So can I say the milliequivalents of B reacted in reaction 1 is how much? N1 V1 minus N2 V2. And now can I say milliequivalents of B reacted will be equals to the milliequivalents of A consumed? Okay. So can I say milliequivalents of B reacted in reaction 1 will be equals to N1 V1 initially taken minus left. This is the milliequivalents of B reacted in reaction 1 and milliequivalents of B reacted equals to milliequivalents of A consumed. So milliequivalents of A consumed or taken, since A is the limiting reagent, entire A will get consumed, is equals to N1 V1 minus N2 V2. Now we know the milliequivalents of A taken initially. From here, can I calculate the weight of A taken initially? Weight of A taken. How do we calculate? We know weight upon equivalent weight into 1000. is nothing but milliequivalents, and this is the milliequivalents of A, that will be equals to N1V1 minus N2V2. We will be knowing the equivalent weight. We'll simply multiply it by equivalent weight and divide it by 1000. We will get the weight of A taken initially. Am I clear, student? Please copy it. Now, the screen is basically related to the concept of back titration. Let's try to do this particular question. 20 gram of a sample of BaOH whole twice is dissolved in 10 ml of 0.5 normal HCl solution. The excess of HCl was titrated with 0.2 normal NaOH. The volume of NaOH consumed is 10 ml. Calculate the percentage of BaOH whole twice in the sample. Let's do it. Student, I'm having BaOH whole twice. Okay, the weight of the sample is given, but entire BaOH whole twice sample is not pure. Now it's reacting with HCl. Product is not important for me. It's given that this HCl is taken in excess. How much milliequivalent is taken? Milliequivalent taken is 0.5 into 10. That is 5 mil. Initial milliequivalents of HCl is equals to 5. Now, obviously this entire HCl will not react in the reaction 1. Some HCl will be left. Now this left HCl is titrated with NaOH. Once again, the product is not important for me. Now it's given this left HCl is completely reacting with NaOH, and they have given the equivalents of this NaOH, that is 0.2 normal and 10 ml. So can I say milliequivalents of HCl left equals to milliequivalents of NaOH, and that will be equals to how much? 2 milliequivalents. What is the milliequivalents of HCl taken initially? 5. So what will be the milliequivalents of HCl reacted in reaction 1? In reaction 1 equals to taken initially minus left, that is 5 minus 2, 3 milliequivalents. Right, student? Now the milliequivalents of HCl reacted in reaction 1 is 3 milliequivalents. Milliequivalents of HCl reacted in reaction 1 will be equals to the milliequivalents of pure BaOH whole twice. Milliequivalents of pure BaOH whole twice will be equals to milliequivalents of HCl, right? Reacted in reaction 1. And how do we calculate milliequivalents of pure BaOH whole twice? Weight upon equivalent weight of BaOH whole twice. Equivalent of weight of BaOH whole twice is nothing but 171 divided by 2. This is the molecular weight upon n factor into 1000, right? That is equals to the milliequivalents of HCl. 3, right? So from here, student, can I calculate weight? And this weight comes out as 85.5 into 3 upon 1000. That's equals to how much? 0.256 grams. Percent purity is the weight. Percent purity, how do we calculate? That's nothing but the weight of BaOH whole twice taken, 0.25 upon 20 gram into 100, right, student? This is the percent purity of BaOH whole twice in the sample. Please do copy it. Concept which we are going to learn is there on the screen, and it is double titration. What do we mean by double titration? 2 times titration, and here we will use certain indicator. Either we will use phenolphthalein or we will use methyl orange. Let's try to understand the setup in this particular case. Student, generally here we take some unknown amount of salts, and generally the salts taken in such titration is mixture of Na2CO3 and NaHCO3. Okay. In the burette, I am going to take one acid since it's a acid based titration, and I will be knowing the normality of the acid taken. Let's take HCl. Okay. And the normality of this HCl is known to me. The normality is N1, right? The initial indicator taken, generally let's assume I am going to take phenolphthalein. Initially, I will take phenolphthalein, HPH. Initially. Student, since this Na2CO3 is present in this beaker, obviously it is highly alkaline, so initial pH will be close to 10. Although this NaCO3 is having a pH range of 8.2, but this Na2CO3 is having a pH range of, in general, above 10. So initially the solution is alkaline, and as soon as I add this HPH, the color of solution becomes pink. The initial color of the solution is pink as soon as this indicator is added, pink color. Now, drop by drop, I am going to add this HCl to this beaker. Okay. Now, student, one thing you need to understand. In the presence of phenolphthalein, NaHCO3 will not react. In the presence of phenolphthalein, NaHCO3 will not react. So in the presence of phenolphthalein, only this Na2CO3 will react with HCl and will get converted to NaHCO3. So let me write that. In the presence of phenolphthalein, HPH, what will happen? Only Na2CO3 will react with HCl and I will have the formation of NaHCO3. Can you tell me the N factor of Na2CO3 in this reaction? Na2CO3 getting converted to NaHCO3, one replaceable cation, right? So the N factor is going to be 1 here. Am I clear, student? N factor of Na2CO3 in the presence of phenolphthalein is 1. Now let's suppose I have taken X moles. So moles into N factor is nothing but the number of equivalents, and number of equivalents into 1000 will be the number of milliequivalents. So can I say number of milliequivalents of Na2CO3 will be equals to number of milliequivalents of HCl. Now for this HCl, I know the normality, and obviously as soon as this pink color disappears, I am going to stop the titration. I will have the complete formation of this NaHCO3, so I can easily record the volume consumed. I can easily note down the volume consumed. Student, basically what happens when this titration starts, acid base reaction will occur in the beaker, condition is alkaline, HCl is get added. What will happen? pH will start decreasing, right? As soon as the pH comes close to 8, what will happen? The pink color of the solution will disappear and I will stop titration. At that particular moment, this entire Na2CO3 will get converted to NaHCO3. Now I will note down the reading here. So I know the normality, I know the volume. So can I calculate the milliequivalents of HCl reacted in this reaction? N into V1. So from here, student, I know the normality of this HCl, I know the volume, I know the milliequivalents of HCl, right? So from here, can I calculate the value of X? Milliequivalents of Na2CO3 reacted equals to milliequivalents of HCl. Now milliequivalents of HCl we know, so milliequivalents of Na2CO3 I will know, and milliequivalents of Na2CO3 is X into 1, that is number of equivalents into 1000. So from here I will easily calculate the moles of Na2CO3. And once I know the moles of Na2CO3, can I easily get the weight of Na2CO3? Yes. So from here, moles of Na2CO3 I can calculate. Na2CO3 taken, I can easily calculate, that is equals to N into V1 upon 1000. Right? Now, in the beaker, this Na2CO3 is also now converted to NaHCO3. Now, I need to change the indicator. Now I am going to take, now the titration with phenolphthalein is over. I know the amount of Na2CO3 taken initially, but still I don't know the weight or amount of NaHCO3 taken. For that, what I need to do? I need to change my indicator, and now I am going to take methyl orange. Methyl orange. Now, in the beaker, I am having NaHCO3 taken initially plus NaHCO3 formed from Na2CO3, and both these NaHCO3 will react with HCl in the presence of this indicator. So I'm having NaHCO3 taken initially plus NaHCO3 formed, and both of them will react with HCl, and I will have the formation of NaCl and H2CO3, but this is not important, plus H2CO3. What's the N factor here, student? Still 1, and Na plus is replaced by H plus. So N factor is still 1. 1. N factor 1. N factor 1. Now, can I write, since this HCl is reacting with both these NaHCO3, so can I write milliequivalents of NaHCO3 taken initially plus milliequivalents of NaHCO3 formed from Na2CO3 will be equals to milliequivalents of HCl. Now, for this HCl, I know the normality. I can easily record the volume of HCl consumed in step 2 of the titration. In the second titration, let's assume the volume consumed is V2. Normality is N. Volume consumed is V2. So can I say the milliequivalents of HCl is N into V2? Do I know the milliequivalents of NaHCO3 formed from Na2CO3? Yes. Here, student, milliequivalents of Na2CO3 reacted equals to milliequivalents of HCl reacted, and that's equals to milliequivalents of NaHCO3 reacted. Clear? And that's equals to N into V1. So milliequivalents of NaHCO3 formed is N into V1. So from here, can I calculate milliequivalents of NaHCO3 taken initially? How much? N into V2 minus N into V1. Now once I know the milliequivalent, let us assume the mole taken is Y. So Y into N factor is the number of equivalents. N factor of NaHCO3 here is 1. So Y into 1 is the number of equivalents into 1000 is the number of milliequivalents, and that's equals to N into V2 minus V1. From here, I can calculate the amount of, or the moles of NaHCO3 taken initially. That's N V2 minus V1 upon 1000. Once I know the moles of NaHCO3 taken initially, I can easily calculate the weight of NaHCO3 taken initially. Clear, student? Please do copy it. Student, now let's solve this question related to double titration in order to understand this concept in a better way. Okay. In the question, it's given 0.4 gram of a mixture of NaOH and Na2CO3 and certain impurities was first titrated with phenolphthalein and HCl having normality 1 by 10 and the volume of HCl consumed was 17.5. Okay. After this, methyl orange is added and 1.5 ml of sample of HCl was again required for the next endpoint. Find out the percentage of NaOH and Na2CO3 in the mixture. Let's try to solve it. Okay. Student, here the base taken is NaOH and Na2CO3. Let us assume X moles of NaOH is taken and Y moles of this Na2CO3 is taken. X moles of NaOH and Y moles of Na2CO3 is taken. Now, in presence of phenolphthalein, presence of HPH, what will happen? Both NaOH as well as Na2CO3 will react. This Na2CO3 will get converted to NaHCO3 and NaOH will get converted to NaCl. So I'm having NaOH plus Na2CO3, both of them will react, plus HCl, and I will have the formation of NaHCO3 plus NaCl. Can you tell me the N factor of Na2CO3 here? 1. N factor of NaOH here? 1. Okay. Now, can I apply law of chemical equivalence? Yes. Can I say milli-equivalents of HCl reacted equals to milli-equivalents of NaOH reacted plus milli-equivalents of Na2CO3 reacted, right? And can I also say, since this Na2CO3 is getting converted to NaHCO3, so milli-equivalents of Na2CO3 will be equals to milli-equivalents of NaHCO3 formed. Am I clear? We'll write it, don't worry. What's the milli-equivalents of milli-equivalents of HCl reacted? 1 by 10 normality into volume. That's 1.75 equals to milli-equivalents of NaOH. Let's add the weight moles of NaOH given is X. X into N factor. Moles into N factor is the number of equivalents into 1000. This is nothing but milli-equivalents of NaOH. What will be the milli-equivalents of Na2CO3? The milli-equivalents of Na2CO3 will be moles of Na2CO3 into N factor. N factor is 1 into 1000. So now I'm having an equation X into 1000 plus Y into 1000 equals to 1.75. Now student, since this NaHCO3 is formed from Na2CO3 only, so can I write milli-equivalents of NaHCO3 formed is equals to milli-equivalents of Na2CO3 reacted, and that's equals to how much? Y into 1000, right? Now, in the beaker, only one base is there, and that is NaHCO3. Now I am going to take methyl orange. In the presence of methyl orange, what will happen? Methyl orange, what will happen? This NaHCO3 formed will react with HCl, and I will have the formation of NaCl plus H2CO3. N factor is 1. So can I say milli-equivalents of NaHCO3 formed is equals to milli-equivalents of HCl reacted once again? And what's the milli-equivalents of HCl reacted in the second titration? Volume 1.5 ml, normality 1 by 10. Okay. So that's equals to 1.5 into 1 by 10. Right? This is the milli-equivalents of HCl. And milliequivalents of HCl reacted equals to milliequivalents of NaHCO3 reacted or milliequivalents of NaHCO3 formed, and that's equals to Y into 1000. So from here we know Y into 1000 equals to how much? 1.5 upon 10, nothing but 0.15. So what's the value of Y here? 0.15 into 10 raised to the power minus 3. Right, student? Okay. We know the value, this equation also. Now, we know the value of Y. So from here, can I say this X plus Y is nothing but 1.75 into 10 raised to the power minus 3. The value of Y is 0.15 into 10 raised to the power minus 3. So the value of X is how much? 1.6 into 10 raised to the power minus 3. Now I know the moles of X, that is the moles of NaOH. How much? 1.6 into 10 raised to the power minus 3. Moles we know. So can I calculate weight of NaOH from here? And that's equals to how much? Moles 1.6 into 10 raised to the power minus 3 into molecular weight. Molecular weight is 40. So it's how much? 6, this much, 64 into 10 raised to the power minus 3 grams. Right? This is the weight of NaOH. Now weight of pure Na2CO3, how much? How much? 0.15 into 10 raised to the power minus 3 into 106. This is the weight of pure Na2CO3. Now we know the weight of pure NaOH and pure Na2CO3. I can calculate the weight percent purity of NaOH and Na2CO3 in the mixture. Am I clear, student? Please do compete. Students, moving ahead, the next type of titration which we need to discuss is iodometric titration and iodimetric titration. Let's discuss it one by one. Student, if I talk about iodometric titration, it's basically the process of conversion of iodide ion to free iodine molecule. Iodometric titration. It's a process in which iodide ion is treated with an oxidizing agent and is getting converted to free iodine molecule. What is the oxidation state of iodine here? -1. Oxidation state 0. So oxidation state of iodine is increasing, right? What's the change? From -1 to 0, 1. What's the atomicity? 1. So N factor of iodine or iodide ion in iodometric titration is 1. Right? This is really important. Now the next one, iodimetric titration. It's a process of conversion of free iodine molecule to iodide ion. The most common reaction which we see is reaction of iodine, liberated iodine, free iodine with hypo, I2 plus Na2H2O3. We will have the product as I minus plus Na2S4O6. I2 plus Na2CS2O3, I will have I minus plus Na2S4O6. What's the N factor of iodine here? From 0 to -1, change is 1, atomicity 2. So N factor of iodine molecule is 2 here. What's the N factor of Na2S2O3? 2 to 2.5, change 0.5, atomicity 2. So N factor is 1. Right? So basically in certain titration you will see first you are having potassium iodide, and this potassium iodide is treated with an oxidizing agent. We are getting a free iodine molecule. Now this free iodine molecule is titrated with hypo, right? And then we'll have the reaction like this. Simply what you need to do, from here you can easily calculate the equivalents of iodine formed. Once you know the equivalents of iodine formed, you can write milliequivalents of iodine reacted equals to milliequivalents of hypo. You know N factor and all these things. You can easily calculate, right? Okay. Right? I was talking about this particular reaction is, if you see this reaction, it's nothing but Iodometric. This one. If you see this particular reaction, CuSO4 plus Ki, I minus is getting converted to iodine. This particular reaction is related to iodometry. Right, student? Shall we move ahead? Let's move ahead. Moving ahead, the next topic which we are going to discuss is all about hydrogen peroxide. Let's first of all talk about the reaction of hydrogen peroxide in acidic medium as well as in alkaline medium. And we'll also talk about what's the N factor of H2O2 if this H2O2 is acting as a reducing agent, and what will be the N factor of H2O2 if this H2O2 is acting as an oxidizing agent. So student, this H2O2 can behave as an oxidizing agent as well as reducing agent. This point is really important. And in both the medium, in acidic medium as well as in alkaline medium. Let's first of all talk about acidic medium. And let's talk about the oxidizing behavior. What will be the product if this H2O2 is acting as an oxidizing agent? So student, in acidic medium, this H2O2 will get converted to H2O. H2O2 will get converted to H2O. So what will be the N factor? -1 to -2. Change 1. Atomicity 2. So N factor of H2O2 in acidic medium, if it's acting as an oxidizing agent, is 2. Clear? What's the product? In acidic medium, if it's acting as an oxidizing agent, means if it's getting reduced, the product formed is H2O. In alkaline medium, H2O2 gets converted to or gets reduced to OH minus. Right? Here also -1, -2. Change how much? 1. N factor 2. So if H2O2 is getting reduced either in acidic medium or in alkaline medium, the N factor is 2 only. Am I clear? Now let's talk about the reducing behavior of this H2O2. In acidic medium, right? In acidic medium, student, if this H2O2 is getting oxidized, the product which we get is oxygen molecule. Right? Acidic medium. Acidic medium, right? From -1 to 0, change 1, atomicity 2. So what the N factor here? Once again, N factor is going to be 2. Even if this H2O2 is acting as a reducing agent, the N factor of H2O2 is going to be 2 in acidic medium. Let's see in the alkaline medium. In alkaline medium, basically H2O2 again gives O2 only, so N factor is going to be 2. So the most important point, whether this H2O2 is acting as an oxidizing agent or whether it is acting as a reducing agent, in all such case, the N factor of H2O2 is going to be 2 only. Am I clear? Okay. Student, whenever you go to lab and whenever you will see the labeling of this H2O2 bottle, what you will find? You will find the concentration written as 10VH2O2, 5VH2O2, 100VH2O2. What does this volume strength or VH2O2 means? XVH2O2 means? Basically it means, if I'm having, let's suppose 10VH2O2, 10VH2O2, what does this mean? It simply means 1 liter of H2O2 will produce 10 liter of oxygen gas, O2 gas at NTP. Okay, now let's try to convert this concentration unit into some other concentration terms like molarity, normality. Okay. Let's write this reaction. H2O2, right, will give me H2O plus half O2. I'm having 10VH2O2, right? Now, so 10VH2O2 means 10 liter of oxygen gas will get produced at NTP. 10 VH2O2 means 10 liter of O2 gas produced at STP or NTP. So what is the moles of O2 gas produced? How much? How many moles of oxygen gas will get produced? That's nothing but 10 divided by 22.4. This many moles of oxygen gas will get produced at NTP. Now, 1 mole of H2O2 is giving me half moles of oxygen gas. So what's the moles of H2O2 reacting? Can we calculate? Let's do it. 0.5 mole of oxygen gas is produced from 1 mole of H2O2. So 1 mole of oxygen gas will be produced from 1 upon 0.5, right? So 10 upon 22.4 moles of oxygen gas will be produced from 1 upon 0.5 into 10 upon 22.4. So what will be the moles of H2O2? Moles of H2O2, how much? 2, and it's 10 upon 11.2. What's the volume of H2O2? 1 liter. Volume of H2O2 it's 1 liter. So what will be the molarity of H2O2? 10 upon 11.2 into volume. That's 10 upon 11.2 only molar. What's the normality of H2O2? That's 10 upon 11.2 molarity into n factor. N factor is 2. So it's 10 upon 5.6. Right? So student, I am giving you a simple formula. If you are having XVH2O2, molarity is equals to X upon 11.2. Normality is equals to X upon 5.6. Am I clear? Please do copy all these things. Now, student, now let's do one questions in order to understand this concept in a better way. 20 ml of H2O2 after acidification with dilute H2SO4 required 30 ml of N by 12 KMnO4 for complete oxidation. The strength of H2O2 solution is perfect. We need to calculate molarity, or we can calculate normality also. No, we need to calculate the volume strength. Volume strength, student. Let's calculate the volume strength here. Volume strength. Okay. Now, I'm having H2O2. It's treated with KMnO4. So can I say milliequivalents of H2O2 will be equals to milliequivalents of KMnO4? What is the milliequivalents of H2O2? Volume into normality. That will be equals to milliequivalents of KMnO4, and milliequivalents of KMnO4 is 30. That is volume into normality, right? So can I calculate normality of H2O2 from here? How much? It's nothing but 30 by 12 into 20, right? So it's how much? 3 upon 24, 1 by 8. Normal. Normality of H2O2 we know now. Once we know normality, can I calculate volume strength? Normality is equals to volume strength X upon 5.6, right? So from here, volume strength of H2O2, volume strength of H2O2 will be how much? 1 by 8 equals to x into upon 5.6. So x equals to 5.6 upon 8, 0.7 V. Am I clear? The volume strength is going to be 0.7 V. Right, student? Please do copy it. Student, now let's talk about this hardness of water. If I talk about this hardness of water, there are mainly two types of hardness. Already we have studied, right? Temporary hardness, permanent hardness. Temporary hardness is mainly due to the presence of bicarbonates of calcium and magnesium. Permanent hardness is mainly due to the presence of chlorides and sulfates of calcium and magnesium. Now the most important thing is calculation of hardness of water. Let's see how do we represent it. Basically, student, it is mainly represented as ppm of, it's mainly represented in terms of parts per million of calcium carbonate precipitated. It's mainly expressed in terms of ppm of CaCO3. ppm of CaCO3. This formula to calculate this hardness of water. Hardness of water is calculated as mass of calcium carbonate precipitated, PPT, upon mass of water sample into 10 raised to the power 6. Okay, now sometimes they won't give you directly the mass of calcium carbonate form, but we have a very important tool, and that's the law of chemical equivalence. We can use it. Sometimes they will give a water sample is there. Let's suppose 1 liter water sample is there, and it's containing x grams of MgSO4, right? And now they may say you calculate the hardness of water. How will you calculate? Can you tell me? First, what you need to do, you need to convert this x gram of MgSO4 into equivalent amount of CaCO3. And how will you do it? You need to convert this MgSO4 using series of reagents to CaCO3. And since everywhere the n factor is going to be same, so can I say milliequivalents of MgSO4, you simply use this formula. Milliequivalents of salt given will be equals to the milliequivalents of CaCO3 of equals to milliequivalents of CaCO3 or equivalents of CaCO3. Now how will you calculate the milliequivalents or equivalents of MgSO4? Given weight upon equivalent weight. What's the equivalent weight? Magnesium 24 and 96, 120, n factor is 2, so x by 60, that's equals to, what's the milliequivalent of CaCO3? Weight we don't know. Let's assume y is the weight upon equivalent weight of CaCO3, that is 50. So from here, can you calculate the weight of CaCO3 precipitated? It's nothing but 50x upon 60. Now you know the weight of CaCO3 precipitated. You know the mass of water sample, 1 liter, density 1 kg per meter cube, right? Or density 1 gram per cc. So basically it will have a weight of 1000 grams. 50x upon 60 divided by 1000 into 10 raised to the power 6 is going to be the hardness of this water sample. Am I clear? Let's move ahead. Temporary hardness mainly due to the presence of bicarbonates, all these things we have discussed. Permanent hardness mainly due to the presence of chlorides and sulfates of calcium and magnesium. And these are the few methods through which we can remove hardness of water. Student, now here I'm having a question, and the question says 100 kg of hard water contains 5 grams of MgSO4. Calculate or find the hardness. Can you do it? Please attempt it. Student, here MgSO4 will be converted to equivalent amount of CaCO3. So can I simply apply the formula? Equivalence of MgSO4 will be equals to equivalence of CaCO3. And what is the equivalent of MgSO4? 5 upon equivalent weight, how much? 24 and 96, 120 divided by 2, 60. Right? So this is the equivalence of MgSO4. That will be equals to X upon equivalent weight of CaCO3, that is 50. So from here, can I calculate the value of X? It's nothing but 250 upon 60. Right, student? Is the calculation correct? Now, once I know the weight of calcium precipitated, can I calculate the hardness of water? Yes, I can do it. Of water equals to 250 by 60 into 100 kg. So 100 into 10 raised to the power 3 into 10 raised to the power 6. 1, 2, 3, 3, 6 entire. So basically hardness of water is 250 upon 6 ppm of Ca plus 2 ions. Am I clear, students? Please do copy it. Whenever they will give you certain sulfate, chlorides, anything if they give you, convert it into equivalent amount of calcium carbonate. From there, calculate the weight of calcium carbonate precipitated. And once you know the weight of calcium carbonate precipitated, you can easily calculate the hardness of water. Weight of CaCO3 upon weight of water sample into 10 raised to the power 6. Clear? So that's all about today's students. I hope you enjoyed this particular lecture. Once again, thank you all for watching this lecture. If you have any doubt, feel free, do mention in the comment box. I'll be very happy to solve all your query.